Okay, I think we can start. So I welcome you all to this session on problem solving and live interaction for the subject engineering mechanics. Before we start, let me just introduce myself. My name is Ganesh Ramaswamy. I'm a PhD scholar working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saronan in the Department of Applied Mechanics at IIT Madras. So the idea behind the session is to solve some perhaps some previous year questions and then address whatever doubts that participants have, and then we can take it from there. So I would urge you to solve the question with me so that it becomes more clear for you. And should there be any questions for you midway, you're more than welcome to stop and ask me, and I'll try to answer it. So let us start. Before we start, are there any questions from the previous weeks that we discussed? If there aren't, then I'll go ahead and start with this session. Okay, I take it that there are no questions from the previous weeks. That is up to virtual work we have discussed. So today we will be discussing the topic for week 6, which is friction. So let us start with the first problem. The question says that a force P, this P, a force P is applied on a roller at point B in order to pull it over this step. We are able to see that there is a step here, and the idea is to pull the roller over that step. What is the minimum coefficient of static friction required between the roller and the step? That is, at this point there will be some frictional force acting, and we have been asked what is the minimum value of coefficient of friction required to make this pulling over possible. And what is the additional information we have been given? We have been given the weight of the mass of the roller is given. Okay, so in order to approach this problem, let us first draw the free body diagram for this problem. First, the idea that is to be understood is, if we want to pull it over D, what is the limiting condition of pulling the roller over at C? That it loses contact at D. Loses contact. This is the limiting condition when it will actually lose contact and get lifted over T. So at this step, at this point of the analysis is what, at this point of the movement is what we are trying to analyze. Okay, so if we were to take this being uh, the disk, okay, now we know that a weight is acting downward. I'm just taking it at the center, that is 10G force, and a force horizontally has been applied, which is P. We know that at point D it has lost contact, because that is the juncture time instant at which we are trying to analyze this. Are there any other forces in the picture? Yes, there is a reaction force at C. We don't initially know what is the orientation of that reaction force, we just know that it exists. So the rest of the problem all depends on how we visualize this force. So we know that if it is applied at point B, we can easily move 10G using the principle of transmissibility. We can move this to point B. This is point B. So essentially we can move this force over. We will have P and we have mg here without changing the external effects. And then we have one more force, that is Rc somewhere at some orientation applied at C. We know this. Now we know for a 3-force member, we are able to see that the roller is a 3-force member here. So for a 3-force member to be in equilibrium, in moment equilibrium, we know when we discussed equilibrium, and it has also been discussed at length in the lectures, that for a 3-force member, force system must be concurrent. Must be concurrent to ensure sigma m equal to 0. So we know that this force has to pass through the point of concurrency, which is this, which is point B. So we know that this is the line of action of that C. It has to pass through that point. Okay, so far so good. So using the principle of transmissibility again, we can use and put RC over here, right? So no confusion so far. So now if I were to go here, just take this and let me just put it here. Okay, now we have correctly put where RC is applied. It is applied at point C. Using the principle of transmissibility, we have transferred it to point B. Now let this angle be theta. I'm sorry. Let this angle be some theta. So naturally this angle also becomes theta. So we can write sigma fx equal to 0 gives us P is equal to RC sine theta. Likewise, sigma Fy equal to this comes from sigma Fx equal to 0. Sigma Fy equal to 0. What does this give us? It gives us RC cos theta equal to mg. So far so good. We have got two equations. Now this is a concurrent force system, so we will not be applying moment equilibrium at this point, at this correct point. However, if we have to lift it over C, what is the limiting condition? That the disk has to roll over C. So the clockwise moment will be created by P, and then we have an anti-clockwise moment created by mg. RC will not participate because RC is applied at C. So let us take the moment at C equaling 0 being the limiting condition. What will this come out to be? Now from the figure we can see that this distance from here, this distance we can easily calculate. It is, if this is taken to be r, this distance is nothing but r into 1 plus cos 45. From the geometry we can see that. Similarly, we know this distance. What is this distance? This comes out to be r sine 45 or cos 45, howsoever we take it. It will actually be r cos 45. So it will be r by root 2. So we can write the moment equilibrium. This will create a clockwise moment. P will create a clockwise moment which is negative. So minus P into R into 1 plus cos theta. And then there will be a moment due to mg which is anti-clockwise in nature, which is positive. Mg R sine theta, which we just wrote it as 0.2 here. There is nothing else because RC will not contribute because we are taking moment about C. So from here we can see that PR 1 plus cos theta comes out to be mg sine theta. So mg r sine theta. So r cancels out and p by mg we get it as sine theta upon 1 plus cos theta. Uh, one small issue here. I will call this theta 1 because this is not that theta which we have defined. Theta 1 is 45 degrees. It is known, it is given in the problem. So I hope you have understood that. So theta 1 is 45 degrees, so we can just substitute simply and we get mg is equal to 1 by root 2 upon 1 plus 1 by root 2, which is nothing but 1 by 1 plus root 2. So p by mg we have got as 1 plus 1 by root 2. Now from these first two equations, we know P and mg in terms of RC and theta. So we can just substitute. We got this P as, from here, we got P as RC sine theta upon RC cos theta, comes out to be 1 plus by root 2, which is nothing but tan theta gives us 1 plus 1 by root 2. So far so good. At point C, let me just draw. At point C, this is what we are calling as RC. Now if we see, there is a normal component to this which will pass through the disk center, and then there is a tangential component to this which is nothing but frictional force at C, and this is the normal component at C. This angle we just define as theta. So tan theta from this figure is frictional force divided by the normal at C. We know that frictional force divided by the normal in the limiting condition is nothing but our mu, coefficient of static friction. So directly we get that mu is nothing but tan theta. Mu is, we have got it as tan theta is a relation we have got, and tan theta we already saw here, that tan theta is 1 plus 1 by root 2. So mu is nothing but 1 plus 1 by root 2. Now this comes out to be 0.4414. So this is our answer to this question. What it asks is, what is the minimum coefficient of static friction required for the roller? So minimum coefficient of static friction required is 0.414. So I hope this question is clear on how we solved it. If there are any questions, please feel free to ask, or we'll move on to the next problem. Any questions? Okay, I take it that it is clear. I'll just move on to the next problem then. So we can see the question says that a weight, this weight of 10 kg is suspended on a rod using identical rings. We have two rings here. If the rod goes like that, we have a ring like that, and these are identical rings on both the ends. So the coefficient of friction between the ring and the rod, coefficient of friction at this interface, mu is given to be what is given in the figure, that comes out to 0.3 is what is given. Considering the connecting strings to be massless, we ignore the mass of these strings. What is the maximum value of distance L before the ring slip over the rod? I hope you are able to picture that as we take this rod further, as we keep the rod and then keep pushing the rings further and leave it, at some point in time it will come and stop because of the frictional force balancing the components of the weight. So we are just asked up to what distance can we actually take it so that it is in equilibrium on its own. So that is the question. So at this point, let us take this. From the symmetry of the problem, we can see that both will be both will be equal, because the problem is symmetric. So let us take it to be T. I have just drawn the how the tension would look from both the ends. That is all. It is not that it is cancelling each other. That is to be clearly understood. So if I take this subsystem, if I were to take this subsystem, I can see that, let me call this some angle. Let us call this theta again. So we can see from force equilibrium that 2t cos theta is nothing but 10 kg into g. So this is one equation we have got. 10g. This is one equation we have got. The other equation, let us consider this subsystem. Let us consider this subsystem and what is happening at that point. So if we were to consider the whole thing, we know that there will be two forces acting on the rod, which is nothing but the weight, which is 10g by 2, 10g by 2, symmetrically distributed. So the normal force essentially at the ring and contact interface, at the ring and rod interface, is nothing but normal force between ring and rod is nothing but 10g by 2. And we have been given that coefficient of friction at that point is 0.3. We have been asked the maximum distance. At this distance, we know that friction will be the, the whole system will be at the verge of motion. So friction can be equated to mu into the normal force using the Coulomb's law. So at this point, what will be the horizontal force? Frictional force. Frictional force will be mu s into 10g by 2. This is our frictional force at that point. Now this frictional force will have to balance the component of tension in that direction. So the component of tension in that direction is, if we just see here, so we have a tension here and we have said that this is theta, and at the normal force at this point is N is given by 10g by 2, and we have a frictional force that will balance. Frictional force is nothing but mu s into 10g by 2. Now if we do the force balance there, we know that this is 90 degrees. So this is into mu. Uh, yeah, this is mu I have written actually. This component 10g by 2 is n. Sorry, I didn't. Yeah, okay. I got the point. I didn't write mu properly. So I hope that is clear. So we have t, t sine theta is to be balanced by mu s into 10g by 2. So everything is given. Now if we see here, we have frictional forces mu s into 10g by 2, and we have t from equation 1. If we take this equation 1, okay, I copy it and I paste it here. So I know that t is nothing but 10g by 2 cos theta from here. I substituted back here. What do I get? 10g sin theta upon 10g by 2 cos theta. This entire thing is t, and then I have sin theta is equal to mu s into 10g by 2. 10g is cancel out, 2 cancels out. So I have tan theta equal to mu s. So from here, theta I can calculate. Friction is given as 0.3. So angle comes out to be 16.7 degrees. From the geometry of the problem, if I know the angle and if I know this, I know that L by 2 is nothing but L by 2 by 2 is sine theta. So L is nothing but 4 sine theta. From the triangle, we can see that. So it will be nothing but I take sine of this angle and multiply it by 4. So I will get the length as 4 sine theta. Sorry about that. Into 4, which comes out to be L comes out to be 1.15 meters. So What is the maximum value of the distance L? L maximum can be 1.14 meters, as we got here, 1.115 meters. Beyond that it will slip, and the equilibrium will no longer be satisfied. So I hope this question is clear. If you have any follow up questions on this, you please feel free to ask. So I take it that it is clear. So these are basic applications of the Coulomb's law, and when to consider that it is at the verge of motion. So that is what we are trying to see here. Now we'll move on to the next problem. In that case, you just see that a truck is parked on an inclined roadside with angle theta as the angle of inclination. So this angle, this is given to be theta with respect to the horizontal. Now the mass of the truck is given as 4.5 tons. So the mass is given as 4.5 tons with the mass center coinciding with the geometrical center. For simplicity, they have provided that it is at the center of the rectangle. In actual practice, if we see, it will be somewhat lower, but for the sake of this problem, we will take it to be at the geometrical center. So the entire width of the truck measures to be 2.5 meters, which is given here. The coefficient of static friction between the tire and the roadway is given to be 0.45. So we know this much. Okay. So the first part says, given that B and H, so this B and this H we have been given, B is 1.85 meters and H is 3 meters. What is the maximum angle in degrees so as to ensure that the truck does not slide sideways? So if we have to analyze this, let us again as usual draw the free body. So we have our force here, which is mg. So from the geometry we can see that this will be mg cos theta, and likewise this force will be mg sin theta. So there will be friction mobilized at this points. We will get friction at this point, and this friction, the limiting value will be when it is at the verge of sliding over it. So we take it that it will be, let us just draw it here once. Okay, so I have, sorry, I have two wheels shown like that, and then I have frictional force that is opposing it. I have mg cos theta here, and this is mg sin theta, and then I know that there will be normal force. From the symmetry, uh, we take it that it is n1. Actually, it will not be equal, that's fine, but as long as we are dealing with the entire system, we can take this to be n1 and n2, but we will sum it up together in order to solve the problem, and both will be at the verge of uh, this thing sliding. So what is the total force that needs to be resisted here? Start one, please. So the total force that needs to be resisted is mg sin theta, and this needs to be resisted by the frictional force that is developed. What is the sum total of the frictional force that will be developed? It will be nothing but mg cos theta. So we can see that the safe angle for it not to slide is tan inverse of mu s, and mu s we know it is given to be 0.45. So let us call this okay, for this case let us call this theta. So we will get this as tan inverse of 0.45, which comes to 24.23 degrees. So far so good. Now if we move on to the next part, it says that same D is given and H is given, and we have been asked to calculate the maximum angle so that the so as to ensure that the truck does not overturn. Now here we can see that at the edge of this point, this will be the point about which point of overturning. So the entire truck would try to tip about that point. So again we have already seen that this is mg cos theta, and then we have here mg sin theta acting. So are there any other forces apart from these that are acting? No, for the entire system I'm saying. So if we were to separate out, we will be able to see that the total force that needs to be countered is by the virtue of the weight. So at this point, when it is overturning, we take it that it has lost contact at wheel set A. So the normal force at A that is acting will not come into the picture. That is to be clearly understood. So the entire weight would be borne by a normal reaction at this point. And since that point is already passing through the point about which we are taking the moment, it will not have a component. So essentially we are seeing that moment equilibrium only entails components of the weight, sine and cos components of the weight alone. The normal force passes through that point, and at the other wheel set, at this wheel set A, it has lost contact. So I hope that is clear. So if we were to take this, we can write the moment equation as such. We will be getting a clockwise moment because of mg sin theta component. So it will be mg sin theta into the, what is the lever arm for that? This will be the lever arm. So if we have to calculate this, this will come to h by 2 plus, this is given, these dimensions are given, so we can just take them directly. It will be h by 2 into plus zero point 0.4. And if we have to calculate the leverage for this component, this is the leverage. What will that come out to be? From the figure we can see that it is b by 2 plus 0.25 by 2. I hope that is clear. Till that edge is what we are seeing. So half of the wheel's width plus b by 2, since b is given with respect to the centers. So we can take this h by 2 plus 0.4. This has to be less because this is the overturning moment. This is what is causing it to go into an unstable state, and the restoring force, restoring moment is offered by the cos component of the weight. So as long as the overturning moment is less than the restoring moment, we are safe. So we are looking at the limiting condition here. So this will be, this has to be less than mg cos theta into, we saw it is b plus 0.25 by 2. So we are this is the overturning moment, and this is the restoring moment. So this should be less than equal to this. So at the limiting condition, we will equate it. So let us equate it. We see that this cancels out. So we get tan theta less than equal to b plus 0.25 by 2, and this whole thing divided by into h plus 0.8 into 2. I have just divided it. So we get this as tan theta less than equal to b plus 0.25 upon h plus 0.8. So this is an important relation we have got to ensure that this does not tip over. Now in this question we have been given b as 1.85 and h as 3 meters. So if we were to substitute, it will come out to be For the limiting condition, we equate it, or rather I would prefer it to keep it like that so that it is clear. Is less than equal to B we saw was 1.85, so it is 1.85 plus 0.25 divided by 3 plus 0.8, so 0.55 is what I'm getting, this ratio. So theta has to be less than equal to 28.93 degrees. So as long as theta is less than equal to 28.93 degrees, individually it will not tip, that we are sure of. So the answer to this question, the maximum angle so as to ensure that the truck doesn't overturn is on its own is 28.93 degrees. But whether we can raise it to 28 is the question. And this is addressed in the next part if we see. So given that B, we have been given that B is 2 meters, what must be the maximum height edge? The maximum height edge of the truck to ensure that the truck is parked safely against any kind of instability. What are the instabilities that are possible here? As we saw, it can either slide or it could tip about point B. So these are the only two possibilities causing it to become unstable. Okay, so in the last this thing we saw that we have derived a relation for containing the tipping action, and we have already seen that the angle to prevent anything from sliding, the truck from sliding, is 24 degrees, and if we notice this happens to be less than our angle required for tipping. So what this essentially means is, as we increase the angle, the sliding would have occurred when we just crossed 24 degrees. It would have already slid down. So there is no possibility for us to go till 28 to ensure that the truck doesn't tip about that point. So this essentially means that our limiting angle for this problem to contain any sort of instability is the governing of the two, which happens to be 24.23 degrees. That is to be clearly understood here. So let me just copy this equation which we have got. Okay, so we have got this equation. B is given. Now here the point to be noted is that theta, which we will take, is the governing of the two, which is 24.23 degrees. I suppose that is what we got. Okay, and D is given. What is H max is what is asked. So we can easily calculate that from here. We can see that tan of 24.23 into H plus 0.8 should be less than equal to B plus 0.25. So B is given 2 plus 2 divided by tan 24.23 degrees minus 0.8. So we get H less than equal to 4.2 meters. So the maximum height to ensure that any kind of instability is avoided when we have a governing angle of the two, which we derived in the previous sections, it turns out that our maximum angle can be maximum height of the truck can be 4.2 meters, given that B is 2 meters. I hope this is clear. If there are any questions, I'm happy to take them now. Are there any questions on what we have discussed so far? If there are, please consider unmuting and asking, or you can. It's clear. Okay. Okay. So with this, actually, I had just pasted them. So these are the same things. If we see, it is the same what we have already solved. It is just a copy of that. So this doesn't add any extra this thing. We have already solved them. Okay. So let us see this question. It says a wooden box lying on an wooden inclined plane. So both are wood. Is observed to be at the verge of sliding. It is known that it is at the verge of sliding. So this is the key for us to. This is the cue for us to take it that our frictional force is equal to mu n, where n is the normal force at that interface. So experimental data related to some other experiment on the same material pair, both being wood, suggests that new dynamic, the dynamic frictional force, static coefficient of the dynamic friction is coming out to be 0.27. Now the question that is asked is, this experimental data is consistent with the observation. Of course, experiment are only observations. They are first, the important thing to see is whether you can validate them, and only after that we are supposed to make intelligent conclusions or inference based on the data we have got, so that we are not doing wrong science. We should understand that experiments are prone to error, but nonetheless they are inevitable for any study. So let us see by drawing the free body diagram. Now again, this I suppose we have done it umpteen number of times, so this would be clear that this is mg cos theta, and we have mg sin theta, and then we have a normal force that is acting. Frictional force, it is because of its weight, it will try to come down, so friction is countering it like that, and it is at the verge, so it is mu static n. So from the equilibrium along its axis, if we were to take x and y, which is already shown here, that x and y is aligned with the plane at 15 degrees. So we will be able to see that n is nothing but mg cos theta, and this will give us that tan theta is mu s, and theta we have already got. So mu s comes out to be tan of 15, which is 0.2667. Okay, and experiment on this material pair is telling us that, is suggesting that actually mu d is 0.27. So would this be possible if I can just, you can just take a, why don't we take a poll on this? So you can just consider with this background, what will be, does the experiment data show us that it is consistent with the observation? So we have a Google poll, you can just take the answers and then perhaps, yeah, we've got one answer already. Okay, so I think that is clear. So what it shows is that what this data is suggesting is that mu s is less than equal to mu d is the conclusion that we are able to draw from our experimental data. But in actual, there have been numerous, again there have been numerous experiments, and since it agrees with many experiments that is taken to be correct, and it is observed that calculations based on that also follows, and we are able to predict the correct mechanical behavior. What it says is that static frictional forces, the coefficient of static friction for any material pair is invariably greater than our dynamic friction. So, which is why this conclusion is not consistent with our observations. So, the answer is false. It is not that we don't have sufficient data to conclude, because we have our background of understanding that static frictional force is invariably greater than dynamic frictional force. The coefficients. Okay. So, If there are no questions, I think I'll move on to this problem, which is an interesting one about self-locking. It's a little bit long, but it is quite interesting, gives us quite a lot of insights. So I hope that self-locking, the you have gone through the lectures which deal with self-locking. So let us look at this problem. Okay, two wedges A and B, these two wedges, both have an angle of 5 degrees. The wedge angle is 5 degrees, and they are having negligible mass is given. Is used to lift a block pushed against a vertical wall. We have a vertical wall here, and it is being pushed against that, and we are trying to lift this weight. This block we are trying to lift up. The lifting operation is carried out by driving this wedge A by applying a force P here. So we are applying a force P in turn that lifts the block is the idea here. So the first condition is that we are driving this and it is lifting. So the magnitude of the normal force and magnitude of the other forces subsequently is asked. So this we can solve by first considering the free body diagram of the entire system. So we have a block like that, and then the wall will be applying one force. Let us say it is N1, and we know that there is a weight acting downwards, which is 15 kg was what was given. So I take it that the force is 15 g. Now this block is trying to move up. So friction always opposes motion. So our frictional force that is developed will be like that. And since it is moving up, or at least at the verge of it, this will be nothing but mu s into n1 at that point. Okay. Now there will be a normal force that will be that the wedge that is driving it will push will apply on this. Let us call that N2. Now let us draw that wedge also. This is my wedge and I have applied P. This is my third wedge which is resting on the floor, and these both wedges are given to be massless, so we need not consider their mass for simplicity. So we have N2 will be applied. Likewise, this will apply some force N3, let us say, and then we have N3. Finally, from the floor, it will offer N4. And on the right side, if we see the problem, it is not in contact. Here, there is a gap. So, there will be no other force that is acting on this. From on this side, I mean. Okay. Now, coming to the frictional force directions. This is trying to move up. The wedge, we are trying to drive it inside. So, if the wedge is trying, the motion, tendency of motion is this way, it is this way, then the friction that will be offered on it would oppose this motion. It is trying to oppose the motion. This is what is to be clearly understood. Now by Newton's third law, it is simple to see that our frictional force direction will be like that. Can we comment on the frictional force direction of this bottom, what is being offered by the floor? I'll just draw it again once. We have N4 acting over here. So this frictional force and N3 together is trying to push it to the right. So it is to be clearly understood that we have a frictional force that will oppose this motion. Okay. Now this again will be mu s into N2. You can see. Actually the angle is only 5 degrees, but I am drawing it in an exaggerated manner. And of course in the question also it has been shown exaggerated so that it is clear. Okay. Now we have this. So likewise we have mu s into N2, and this will be mu s into N3. So by Newton's third law, again mu s into n4 n3. Can we say that this frictional force which is acting here, can we comment on whether it will be limiting or not with the data that has been given? Is our question. This is the crux of the problem. So we know that this wedge is being driven. This wedge, this wedge is being driven to the right, and this is being driven. This is being lifted. We don't know any other aspects to the problem. So this we cannot conclude. We will simply take it as F for now. We cannot conclude on whether it is in the limiting condition or not. So this is something to be clearly understood. Rest is straightforward. We have body 1, we have free body 2, we have free body 3. So if I just take it, now I can simply sum up the force equilibrium for body 1, body 2 and body 3. That will give me some relations. So force equilibrium for body 1, if I write. So sigma Fy equal to 0 gives me, if that is 5 degrees, this is also 5 degrees. This is 5 degrees. That's what is given. So from here we can see, we can add up. It will be what? N2 cos 5 minus mu s N2 sin 5, because this component will be pushing it down. What else is there? Minus mu s N1, this force, this force. Then we have to account for the weight itself, minus 15g. Are there any other forces in the vertical direction? No, that's about it. Then let us also write for the horizontal direction. We will have N2 sin 5 plus mu s N2 cos 5, and this is opposed by N1, minus N1 equal to 0. So we have two equations and two unknowns. So this we can just cast as a, maybe as a N1, N2, and then we'll have this 15g we will get here. The other one is 0. The coefficient of N1 from the first equation is minus mu s. Mu s from the question we know, mu s from the question is given to be 0.2 for these interfaces. And this is to be kept in mind that here it is different and here it is different. So both these we should account for properly when we do our calculations. Okay, so it is nothing but minus n1. So it is minus, the value was 0.2. 0.2. Let me draw this a little bigger. Then for n2 it is cos phi minus 0.2 sin phi. Cos phi minus 0.2 sin phi. In n2 it is minus 1, and here the coefficients of n2 are sin phi plus 0.2 cos phi. So we can simply solve this. Cos phi minus 0.2 into sin phi minus 1 sin phi plus 0.2 into cos phi. 15. So if we call this, let us say A, this is B, and this is our unknown X, and X is nothing but inverse of this into B. So we will get, from here we get N1 N2 as 45.73 and N2 as 159.68. Okay, so we have solved at least for two of the forces. N2 we know, N1 we know. Now we'll move on to the second free body. If I can just copy this, put it here. Now for the second free body, we'll write the equilibrium equations again. See, we can see that this mu s and this mu s is same, and there are no vertical forces other than these two that are applied. This doesn't belong here. This belongs to the third body. I just got copied. So vertically there are no forces other than this. Only N2 and N3 exists. And we are able to see that all the angles are also same. The angles of inclination are phi degree for both, and mu s is also same. So quickly we can conclude that N2 is nothing but equal to N3 from vertical equilibrium, because of the symmetry of the problem. The angle being same, mu s is same, and there are no other forces in the vertical direction. So we can say directly conclude that N2 is equal to N3. So this will simplify our work when we write it for the horizontal equilibrium. Horizontally we can write, since this is also N2 is equal to N3, I'll just write 2 into one of the components I'll write. So we are able to see that this will again be 5, 5, this will be 5, 5. So it will be sine 5. Let me take N2 also common, minus 2 N2, because N2 we know, let us express N3 also as N2. It will be sine 5. It is in the this direction, and the cos component is also in that same direction, which is opposing P. 5 is equal to 0 is what we get here. Okay, so P we can directly get as 2 into sine 5 plus 0.2 cos 5. And N2 we know, N2 we have it as 159. So P comes out to be 2 into 159.68 into sine 5 plus 0.2 cos 5. It comes out to be 91.46 newtons. This is the force required to drive it inside, so as to lift that weight. So far so good. Is there anything else that we have not solved for? We still don't know N3 and N4 and F. Most importantly, we don't know F. Okay, let us consider the third body now. For the third body, let me again copy this. Let me add another page. Now we have established that N2 is equal to N3 and both are equal to 159.68 newtons. That is what we got. N2 is 159.68 newtons. Yeah. Okay. So if we write the force equilibrium in the vertical direction, what will we get? Minus, little bit side, minus N3 cos phi and we have the frictional component will have a force facing along N4, so it will be uh, mu s N3 sine phi, which will be plus N4. And since the wall is horizontal, since the floor is horizontal, our friction will be along that and it will not have any vertical component. This comes out to be 0. So from here we can calculate what is N4, because N3 we know it is equal to 3 into 0.2 is that frictional force. This coefficient of friction is still 0.2. I think it was 0.2. Just confirm once. 0.2, yes. So it is 0.2 sine phi minus cos phi. So N4, let us calculate. N3 is 159.68 into 0.2 into sine phi minus cos phi. I'm sorry. Sine phi will not have, just made one small mistake there. It is actually sine phi minus to 0.2. So it is minus plus cos phi. Yeah, I had written it the other way around. I'm sorry about that. Sine phi. So it is 0.97 times of this. So it comes to 156. Why I got it? Because I figured out it was wrong because I was getting a negative value, which is not possible here. So, okay. So N4 we are getting as 156 newtons. Okay. All right. So from the question, we can see that from this image, we are able to see that our mu s at the bottom is 0.3. Let us find out what this comes out to be. Oh, the figure didn't get copied. Okay, never mind. For the fourth one, we have N4 is this. Let us write the horizontal equilibrium also. So it will be N3 sine phi plus 0.2 N3 cos phi is coming out to be F. So if we calculate this, it is nothing but 159.68 into cos phi plus 0.2 into sine phi plus 0.2 cos phi. Sorry, there is a little bit of mix up here. It is sine phi plus 0.2 cos phi. So F comes out to be sine phi plus 0.2 cos phi into 159.68. It is 45.73 newtons. And N4 we have got. Now if we take this to be the limiting value, let us calculate the limiting value. We know that mu s for the floor is 0. What was it given to be? 0.3 is what is given. So it is 30% of the normal force is what is being said. Is this possible to have 156.28 into 0.3 comes out to be 46. So we can see that our mobilized friction in this problem is less than 46, just nearby but still less. So it is possible to have motion like this. That is, it is possible for us to apply without moving the bottom block. We are able to apply and able to lift the top block. So it comes out that it is mathematically and physically possible. Okay, there is another way to look at this. if we simply considered, let us say, if we simply considered this entire system as one, we know that our mass of wedge A and B are to be neglected. That is given in the question. So what is the total downward force that is acting? The total downward force that is acting here is 15 G. We know that. And we know that both the wedges are not in contact with the wall. Only the top block, which is actually being lifted, is in contact with the wall. So another force that is acting downward is mu s into N1. And all this is being countered by the floor, where we got N4. So we could have simply solved this question even by considering the entire system, since we have seen in equilibrium that once a system is in global equilibrium, and we analyze each of the subsystems to be in equilibrium, we can go either way. We can either analyze it globally or locally in order to arrive at our values. Same goes for the horizontal direction also. We see that P is applied from the left to the right. We see that this P is applied. This will be countered only if P is applied like this. This will be countered only by our frictional force which we took and our N1 which we took. So we will be able to calculate our values even without having to calculate, that is without having to consider each and every subsystem. We can calculate some of the values considering it to be a global system also. So that is, yeah, yeah, sure. So this we have seen that these are the actual forces that are being applied in the vertical direction. So we know N1. N1 we calculated. One would have to be calculated, of course, because if we see here, what are the unknowns? P was an initially, P was an unknown, P was unknown, F was unknown, and then we had N1. This should be N1. So we had N1 to be unknown. Okay, yeah, just a minute. So we know that our forces only come into the picture when we separate them out. So it is something to that effect. And I'm consciously trying to avoid this. I'll make this longer so that it becomes clear that there is no contact between these two. So we have N1, then we have mu N1, mu S N1. The total system's downward force is 15G only because these are weightless, is the assumption here. Then we have N4 here, we have P here, and then we have F here. So once we calculate, once we are able to find out N1, rest of the things we will eliminate one unknown. So there will be only two unknowns remaining. Sorry, we will be having four unknowns initially. So at least we have to solve for two, and then we can solve for the rest based on this. So why don't we go ahead and do that? We have N1. N1 we had it as, we calculated it somewhere 45.73. So we had, yeah, local system, yes. Yeah, because globally, if you see, you have to account how many unknowns are there. So there are four unknowns, which we cannot solve with the equilibrium equations. So that is why we are separating it out. Once you are able to get at least one of them, then you can solve for the rest based on a global system. If, let us say, if this was the question and they were asking just for N4 and N1, maybe just the boundary terms, then there is a possibility that you could solve it globally. There's just another way to look at it. Yeah. Yeah, you have to solve for N1, but only for N1, right? You don't have to solve for N2 and N3. local system. Or if there is any constraint given about F, given that the bottom wedge is also at the verge of motion, then you know F directly. In such a case, you will be able to calculate N1 based on just horizontal equilibrium. But since that was not given here, and we are not sure that whether friction has reached its limit or not, we have to dismantle it and analyze it. Depending on the constraints of the system, global analysis is also possible, is the idea I'm trying to convey. But of course, it is a subjective thing, it might not be possible always. But this should also be explored as an alternative to solve the problems quickly, is the idea I'm trying to give. I hope that is clear. Okay. Okay, so are there any other questions other than this? Actually, I was expecting this question to take much longer, but since we didn't go by eliminating the coefficients and did it using by inversion of matrix, it turned out to be a little easier. You can also learn this, and in case you don't know, you can also do it this way, and try to solve equations quickly if it is permitted to use such a calculator in your system. So other than this, I think I have covered for the most part whatever is being taught in the lectures. So if there is anything else that if there are any other questions, I'll be happy to answer them. Otherwise, I'll call it a day, and perhaps we can meet next Friday on for the discussion on. Yeah, we'll be stepping into dynamics starting week 7. A little bit of belt friction will come, but for the most part, it will be dynamics, in where we will be dealing with particles, particle motion, how to analyze a system as a particle, when to analyze, when that assumption falls apart, and when we cannot know when we can no longer analyze systems as just particles, and we need to bring in rigid body, a system of particles. So all this we will be seeing it in detail, and I am aware that generally dynamics portion is considered to be a little formidable for people who to start with. So it is actually a misconception. If the concepts are clearly understood, I don't think there is any problem in handling dynamics. So I would encourage you to attend the sessions, and if there are any questions, I'll be happy to take them, because mostly the questions where confusion where it arises is which is the angular velocity to take, and when it can be considered to be inertial, non-inertial, where to fix the rotating frame of reference. Questions like these, if they are clearly understood, it will go a long way to help you score in the exams, as well as get a clear understanding of the subject matter. Because we cannot live in statics alone, we are dealing with systems that are moving, that are rotating. Every day we come across them. So it is important that we learn engineering mechanics in a comprehensive manner, so that we don't confine ourselves to statics alone. We also explore dynamics and understand what are the fundamentals. So that we will be discussing starting next week. But other than that, if there are any other questions on what we have discussed so far, not related to friction also, if you have any other questions from maybe virtual work or topics discussed before that, beams or trusses, I'm happy to take them now. Or you can also ask them in the forum, as we have already discussed a number of times. So are there any other questions? I hope my delivery is clear, and I'm not going too fast, or I'm not skipping steps, and I'm at least articulate enough to explain what I'm trying to say. So if there are any feedbacks that you have on that front also, I welcome them, and I'll try to, perhaps if there is any shortcoming, I'll try to address them starting from the next session. If there are, you can please bring them up. Okay. So my delivery is fine. At least can I get a confirmation on that, so that okay, it's fine. Okay. Okay. And are you finding these sessions of any help? Is there any value addition to the subject understanding, or should I select some different kinds of problems? Uh, because I'm basically, when I'm selecting problems, I'm trying to cover whatever topics are discussed, and slightly try to include some challenging problems also, which are generally considered to be challenging, not to be mistaken that it's very challenging, which are generally conceived to be a little higher, so that one gets a clear understanding on how to approach those problems also. If there is any feedback about what questions I should take or select, or whether I should go a little more conceptually deeper, please let me know, and I'll try to incorporate them starting next week. Because from the next week we will be discussing dynamics, which is altogether a different ballgame. So I would urge you to brush up a little on cross products and dot products, so that we can take it from there easily. Other than that, I have nothing more to say as of week 6. So if there are no further questions, I call it a day, and I thank you for attending this session.